Good morning, mathematicians. How we all doing? Time to get back to it, I guess. Langlands parameters? More Langlands parameters? I guess so. I guess that's what I'll yap about today. Maybe I'll just put that as Reddit. Yeah. Ooh, successful reading group. Nice. Chapters 1, 2, 3, and 5. All the exercises. Congratulations. Okay. Let's see. Representations of the V group. So, Langlands parameters. We're moving towards Langlands parameters, but why Langlands parameters? Well, this was all spawned out of a question because we talked about, in general, there's this theme in Langlands of matching automorphic representations to Galois representations. So then it was like, well, why do we... What's up with the V group? There's a question of like, oh, is there a global V group? And I guess really, well, okay, there is... I don't think we have a definition of the global L group, and we want to have, like, I don't know, better definition of global Langlands parameters, but wait, maybe there is. Wait, is there a global V group actually? I didn't think so, but no, I suppose. Wait. Oh, I'm crazy. There is also a global V group, which basically works the same way. I should have known. I should have known. That probably fits into global class field theory as well, right? Yeah. Okay. Well, anywho. Well, there you go. Even I learned something new on my streams. So, anyways, we do have a local V group, though, which we were talking about as our local approximation to Galois representation. So locally, we can still see it, hello, Arad, as a correspondence between Galois representations and automorphic representations, but we see it by passing through this V group. So one part of the correspondence, then, I should say, is that sort of like one-dimensional Langlands, which is local class field theory, says that hello, Adib. Glad that you're back, and I'm back. So, there are so-called the unramified characters. So these are characters that are trivial on the ring of integers. So, for example, this would be like ZP cross, or the multiplicative group of invertible elements in the ring of integers. Like if this was QP cross, then this would be ZP cross. And so well, F cross actually factors into, you can choose a generator. What's a uniformizer, and times OF cross, and basically this part just ends up being isomorphic to the integers because you're just generating by integer copies of this, and this part ends up being isomorphic to a finite field of order Q, I guess I should write, times the multiplicative or the additive group. But anyways, so if you're trivial on here, then all you need to do is tell me what complex number you send this Q to, or sorry, you send var pi to. And so, well, the p-adic absolute value of var pi is Q. And so the p-adic absolute value of var pi to any complex number, will be Q to the S, and then this entirely determines a character, which I'm going to call nu to the S. So I'll call nu for this character, right? So then these characters, through the local Langlands correspondence, or again, at this point, it's basically just class field theory, these are characters of GL1, and so they should correspond to Langlands parameters, so maps out of here into GL1C, but actually no interesting part happens here on the SL2 factor. I'll explain maybe in more detail in a second. So this really does just boil down to a representation of the V group, which is to say pulling back a Galois representation. And how is that given? Well, remember that the V group is generated by a choice of Frobenius and the inertia subgroup. And so we can define a character here, which I'll call omega, where omega is, well, that will be trivial on the inertia subgroup. Hello, Lola. And it will send the Frobenius to Q. And so sort of one-dimensional Langlands. Well, okay, this isn't full one-dimensional Langlands because I've only talked about the characters that are the unramified characters, but okay. So we have a bijection between, let's say, a bijection between characters, unramified characters of GL1, sending nu S to the character omega S. So that's the main bijection for one-dimensional Langlands. Well, okay, then there's the second part. There's the ramified characters as well. Langlands proved. We can all go home now. Yeah. Yeah. Well, now it's time for the two-dimensional case, which is proved for GLN, but a lot more to do. Yeah. So, okay. So that's one-dimensional. That's one-dimensional unramified local Langlands for GLN. Mind you, I guess that's the only one-dimensional case. So now we need to, so I'm almost ready to tell you. Here's how you form all of just the Weil group representation. So these are not yet Langlands parameters, but you. So you have first a representation of Galois type. So that was something that got pulled back from a Galois representation. And then you can twist it by one of these characters. So you take the tensor with one of these omega s. And so this gives us basically all of our infinitesimal parameters. How hard would be going through Humphrey's Lie algebras and representations? Well, it depends what you mean by that question. Like, are you asking me to go through it on YouTube? Because I've thought about doing that before, but only so many hours in a day, and I want to write my thesis. Are you asking for yourself to go through and read it? Well, that totally depends. If you're a researcher in Lie algebras and representation theory, it's probably pretty easy for you. But I'm guessing that you're asking me because you're not a researcher in those fields yet. But again, depends on your background. If you have like no linear algebra experience, also then it will be impossible. As a student, maybe a grad course. Yeah, for a grad course, definitely. Yeah. I think that's a good book, and I think it's worth going through. I don't think it's anything too crazy, really. Yeah, in my opinion, it's not. You need enough background, in linear algebra, and you should maybe care about what a group, Lie group is, or algebraic group, or Lie algebra is, but course would cover some of the chapters. Yeah, probably not the entire book. Yeah. You're a second-year undergrad pursuing a math major. What would I suggest on how to improve in analysis or writing proofs in general? As a first exposure to representation theory? No, I don't. I think you should start with representations of finite groups before reading Humphreys. I got a copy of Howe's book because it's really cheap from Springer right now. So that's sort of been like my bedtime reading, reviewing some representations of finite groups. But there's Fulton and Harris, which there's definitely books out there that could have more exposition. But they have representations of finite groups and Lie algebras and stuff. But for this question about how to improve in analysis or writing proofs in general, I don't know what specific advice I have other than, the two main things you need to do is write a lot of proofs and read a lot of proofs. That's mainly it. You got to read a lot of proofs from other people to see how other people write proofs and then imitate that. Or, if you're going through a book and you're reading a book, try and rewrite the proofs in your own words, or if there's details missing or that you feel are missing that you would, you're like, oh, I had to think for a while to fill in this one sentence in the proof. Like, write out your own proofs like that. Yeah, those are really the main ways. And of course, take seriously the feedback you're getting from your TAs or your professors who are grading your papers, and go to office hours and discuss with them about how to improve your proofwriting. Yeah, those would be the main things I would say. Yeah. Your rep theory course in undergrad was so nice. Started with representation of associative algebras. Oh, interesting. Before specializing to group algebras. Oh, yeah. Yeah, that's true. I never thought about going through it that way, but I guess you could go through it that way. You could even approach it from like module theory first, and begin with modules and then specialize down from there to like group algebras of finite groups and other thing. Oh, and you also touched universal enveloping algebras. That's interesting. It makes sense, though. Yeah, I certainly haven't encountered it presented that way in the wild. Okay, so where are we here? Right. So these are all of our representations of the Vey group, our infinitesimal parameters. Or really, we could take direct sums of these. So like you could have two different twists, of two different Galois type representations and so on. You understand what goes on in the classes. You also explain it to your peers quite often. That's an important thing too. I was going to say, you should, having your peers, you and your peers read each other's proofs. If you and your peers can understand each other's proofs, then that's, a good sign. But your grades have been really low. Well, does he give you more specific feedback than that? So I would, I don't know. I would try and press him for more specific feedback. Improve your writings of proofs. Like, is there feedback on the assignments? Or the notes on the assignments? Or when you go to his office hours, like, I don't know, press him for details and ask him specifically, I mean, you should be like holding your proof up to the textbook, and it should look better than what's in the textbook actually. So if you write a proof like Rudin writes a proof, I'd probably take off marks for not having enough detail. Depending on the proof sometimes. So, I mean, not really. He just said improve your proofs. Okay. Well, I don't know. Then it's hard to, I don't know. It's hard to say without, looking at your proofs. I was running a series for a while where I had people submit proofs. And then I said I would roast people's proofs, but then it never ended up being that much of a roast. But I do have a couple videos where I go and review people's proofs and talk about how I think they could improve. But I've stopped doing that because I got busy. Maybe I'll get back to it at some point. I do have a bunch of submissions that people have sent me that I haven't reviewed. So I've got material there. I could start it up again. You could submit it to there. Yeah. Yeah, but outside of that, yeah, I don't know. I don't know. Yeah. Because kind of, yeah, I don't know. In order to improve your proofs, like, kind of need someone to tell you what you're doing, be more specific about what you're doing wrong. Um, yeah, I don't know. I guess in the interim, I would just say, I don't know, carefully read over your proofs and really like compare it to the um, way it's written in the textbook. Like, grammar and neatness are important. You know, um, yeah, like I said, give your proof. Give your proof, say maybe after when the assignments are handed in or something. Give your proof to one of your peers, and ask them to like read it and see if they understand it. And so then and get feedback from them. If they're like, oh, I don't understand this part or that part, well then that'll give you a clue as to where you need to be putting in more detail, perhaps. Yeah, outside of that, I'm not sure what else to suggest. You could always find maybe there's a mentor, an older undergrad or grad student that would be willing to look at your proofs. You could always get a tutor. I do offer tutoring, but I charge a lot of money, so you should try and find it for free first. Speaking of Lie algebras, to give a map from SL2C into an algebraic group, such as GLN. Do I have any advice for dealing with dead ends in research? Progress stalls. Things seem stuck. Oh. Give up and cry. I'm kidding, kind of. Well, yeah. What can I recommend for getting stuck with research dead ends? Because I've kind of hit some. I mean, eventually I managed to get past them. It's basically I just unearthed references that everyone forgot about when I asked them, but then they turned out to exist after all, and then I didn't have to solve the problem myself. Yeah, I don't know. There was a while where I was kind of stuck on. I didn't know how to carry out one part of my thesis. And so I kind of tried pivoting for a bit with my supervisor. We were brainstorming ways I could pivot. So I started, I don't know, brainstorming other ideas for papers, just related ideas I'd come up with along the way. That's when I wrote some code to compute some of these, stocks of these perverse sheaves. Yeah. So I worked on other things like that for a while. Yeah. I mean, I guess general advice, it's always good to have a couple irons in the fire. Um, have some sort of side project you can work on for a while you're stuck. Or, yeah, I don't know, reach out to other professionals, other mathematicians in the field, and see what they say. I don't know, talk to your supervisor first, but be like, oh, I was thinking of reaching out to so and so, and something like that. Yeah. Would I ever leave Canada? Yes. Well, I was just looking at mathjobs.ca last night. There's a lot of, yeah, a lot of non-Canadian opportunities out there. But yeah, I mean, I do think it would be cool to live somewhere totally different. Um, for last while, I was thinking, I was like, oh, could be cool if I got a postdoc in Europe or something. Um, it'd be fun. Go live in a totally different country and really absorb it. Like, for the longest time, I hadn't been planning on staying in Canada. I assumed I would be in the States at some point because of just there's a lot more universities there, so probably, statistically more likely I'm going to pick up a postdoc there or something at some point. Or if I went to industry, there's like probably big cities like New York or something if I wanted to go make a bunch of money. Yeah. But I do also really like the idea of moving to Europe because then it's very easy to see a lot of countries. They're very nearby. I find travel just really impacts me a lot. I'm a lot more conscious of the ways that travel impacts me now. So it'd be great to be in Europe where everything's really close by and I could go travel places and not have to go too far. Yeah. But Canada's pretty good actually. I've been thinking about that fact lately. I do like Canada. So, I don't know. I don't know where I'll end up long term. Try some other places and we'll see how it goes. Yeah. So for SL2C, gosh, what's a nice way to explain this? Well, so remember that the Lie algebra of SL2C is generated by these three elements where E bracket F is H, H bracket E is 2E, and H bracket F is minus 2F. And I claim that these relations are enough to completely determine the Lie algebra. So we could probably get a Lie algebra homomorphism here just from exponentiating, a Lie group or algebraic group homomorphism from just exponentiating some homomorphism from SL2C into GLNC. So really what this amounts to, though, is basically just picking an element H, an E, and an F in here that satisfies those relations. So, well, how do I say this? There is more to it than that. Maybe I can just jump ahead to there's the classification of irreducible representations of SL2. And I think we've talked about this on the stream like a long time ago. We talked about weight spaces, weights and roots, and stuff. And sort of the punchline of that whole thing is that there's like, for each dimension n, we have a unique irreducible representation, which I'll call Sn. Well, I mean, what I said here is still true. So through this correspondence between like triples here, this means that choice of n or this choice of like irreducible representation should correspond to picking some E in the Lie algebra here. And in particular, notice that E is nilpotent in SL2C. So it turns out that so we should expect the same thing of E. So don't I need the domain to be simply connected? That is, yep, and the domain is simply connected. It's GLNC, not GLNR. So it's simply connected. Wait, simply connected? Simply connected? Wait, does it need to be simply connected? No, because I mean, you can still. I see what you're saying. Well, you can still like, if you exponentiate it, it would just land in the connected component. Or wait a second. Now I'm getting myself confused. No, I don't think you need. Oh, that's my phone. That's my alarm. Time to wake up. Wait, am I crazy? Hang on. Exponentiation Lie groups. Yeah, I don't think you need any connectedness stuff. Yeah, I don't think so. Maybe I'm wrong, but I don't think so. And so ultimately, the SL2 factor, so this amounts to so we can construct a homomorphism from here into GLN, except what's a good way to explain why this is true? Perhaps this makes more sense from there's a slightly different perspective one can take on the V group, but let me just say that for us, such a homomorphism will be a pair lambda n, where lambda is a representation of the V group, n is some nilpotent element of the Lie algebra of GLN. And so those two things together would give us some homomorphism, but now we're going to impose one extra restriction, and that is basically if you conjugate, if you look at conjugation by lambda, then this n will be in the Q eigenspace. Okay. Let's look at an example. So what if we took our, so remember our lambda factors as omega s tensor some Galois type representation. Well, to make life nice and easy, I'm going to pick this to be the two-dimensional trivial representation. No, that's a lie. Well, it'll be a direct. Okay, let me say this. It'll be lambda will be a direct sum of these things for different choices of Galois type representations and different twists by S. But SL2C happens to be simply connected. Yes, that is true. But SLN in general shouldn't be. I think SLN is simply connected. Yeah, SLNC is simply connected. Spin representations. Is that true? Setup. SO. Yeah, the spin representations. It looks like those come from SO, not SL. Yeah, SL is simply connected. SLNC is simply connected. Pretty sure of that. So if we take each of these lambda I to be the one-dimensional trivial representation, so basically I'm going to take this one. This is going to be omega 1/2, direct sum omega minus 1/2. Right? So basically we could say, like, as a matrix even, lambda of W, this representation is going to be given by omega W to the 1/2, omega W to the minus 1/2. Right? We've chosen a representation. Basically, it's going to be trivial, right? This will just be the identity matrix for W in the inertia subgroup, and the entire V group is just generated by the inertia subgroup and our choice of Frobenius. So it suffices to just let me say it this way. I want to know, what are all my Langlands parameters? Into GL2C that have this, that are determined by this infinitesimal parameter. So basically, by what I said above, that just boils down to looking at all the nilpotent elements in the Lie algebra of GL2 and asking which of those lie in the Q eigenspace of conjugation by this matrix. But that matrix will just be the identity for all W and IF, and otherwise it's generated by powers of Frobenius. So I really just need to check conjugation by this matrix, by lambda at the Frobenius element. But the Frobenius element is exactly the thing such that omega at Frob is Q. So Q 1/2, 0, 0, Q minus 1/2. Oh, maybe I forgot to mention this earlier, but what is Q? So F is a p-adic field, and so it's an extension of a finite extension of QP. And then the ring of integers. So basically, if we take the prime ideal in its ring of integers, which sits over the prime ideal generated by P in the ring of integers of QP, well, this latter thing, so this is a field, and this latter thing is isomorphic to the integers mod P, the field of integers mod P. So in other words, this thing must be isomorphic to the field, the finite field with P to the n elements, and Q in this case will be that number, will be that prime power. So that's important. Right. And so finally, we just check what are all possible matrices given by, so I'll just write lambda f. We conjugate an arbitrary, the Lie algebra for GL2 is just all 2 by 2 matrices. So we conjugate this, we see that we get x, q, y, q inverse z, w. And if this is in the eigenspace, hello, Mr. L. We're almost done for today. But we're combining some Lie theory and some number theory to compute some Langlands parameters. So if this matrix is indeed in the Q eigenspace, then these two matrices should be equal. But the only way that can be true, since Q and Q inverse are non-zero, the only way. Wait a second. Q eigenspace. Wait, have I done something crazy? Q1 half. Oh, sorry. Right. We want it to be in the Q eigenspace, so it should be Q times this matrix. That's what it is. So we see that the only possibility is that this upper entry is non-zero. And so we get either the zero matrix or this matrix where we have a non-zero entry in the upper corner. And these two things correspond to two different representations of SL2. So, a priori, it seems like there's infinitely many choices, right? Because there's infinitely many non-zero complex numbers here. But if you take the SL2 homomorphism corresponding to the zero matrix, as you might guess, we get basically the two-dimensional trivial representation. And if we take the SL2 representation corresponding to the non-zero thing, then we get the two-dimensional irreducible representation of SL2C. This doesn't, up to isomorphism, it doesn't depend on the choice. Okay, so one final thing I want to highlight, and this may seem very silly. Well, maybe not at all. Maybe this won't seem silly. So fixing our lambda as above, we asked ourselves, what are all the possible Langlands parameters I could write down that have lambda for its infinitesimal parameter part? And basically, we found that even though, if we want to go right up to isomorphism, there is a difference. But before we sort of collapse things up to isomorphism, we actually had a variety. Really, we got a copy of the collection of Langlands parameters with infinitesimal parameter lambda could basically be identified with these upper triangular complex matrices, which is basically just, affine one space is just isomorphic to a copy of the complex numbers. And in particular, we found that there was a way, but then once we looked at up to isomorphism, we found that there was a way to sort of stratify this variety into two pieces: the zero matrix and those matrices where the entry is non-zero. Or if I chose to write this in terms of notation for the complex numbers, it's basically breaking up the complex numbers into zero and the non-zero complex numbers. But where have we seen this stratification before? Well, last week when I was yapping about D modules, we did a whole bunch of computations for D modules and this stratification. So that's where I'm going to end things for today. Time to get to work. Time to work on my thesis. Got to go scan some quizzes and start grading them. And I'm going to try... I've been doing the Norwegian 4x4 method to train VO2 max. But I think I'm going to do that every second week. And today I'm going to get back to doing sprinting. Because I read something not too long ago that said, like, most people after 30, like, never sprint in their life again. And I was like, I don't know, that struck me. So I was like, I'm going to do more sprinting. Okay. So go improve your VO2 max and then prove some things.